some time in the last class talking or trying to develop this notion of these operators that intrinsically satisfy the properties of either fermions or bosons, and think that actually, according to a current understanding of the nature of particles whose transport we are tracking in this course, is the probably the best, or rather the true mathematical structure that underlies their behavior, at least in the framework of our current understanding of quantum mechanics. And so let me just summarize a few things, and I do want to make a connection today to many of the transport concepts we are going to discuss for the rest of the course. Just to be very clear, in the last two classes have been trying to develop some notions of or these mathematical tools. I haven't talked much about transport in the last two classes, and I think now as we get comfortable with these concepts, it will be somewhat simpler to visualize the phenomena, physical phenomena now with this mathematics behind us. Okay, so if I were to summarize the discussion in the last class, starting from this idea of Dirac's notion of creation and annihilation operators for harmonic oscillators, we actually generalized it way beyond an harmonic oscillator. We said that any quantum system I can think of it as if I have a certain number of states of a quantum system, eigenstates of a quantum system. It could be electrons in a semiconductor. It could be photons in a cavity of a laser. It could be phonons inside a nanowire or a nanotube. Regardless, whichever system we look at has certain allowed energies, and whatever physical phenomena we are looking at, be it thermal conductivity, electrical transport, specific heat, whatever physical property we are looking at is or changing with the voltage. All those changes are occurring because the number of particles that are in these states, maybe there's one here or one there, they are changing. The number of particles are changing in this, the distribution in these states are changing. And these creation and annihilation operators are the ones that keep track of what is the change in which state. So that's your index or a pointer to the states, and saying it's just and as we apply a voltage, as we apply heat to a solid or or moved spin through, these numbers are changing, and we are keeping track of these changes through, the mathematical tool we just discussed was this creation annihilation operator. So a state like this, we said we are going to write it in an occupation number format, where if I have energy state 1, 2, and so on, with an energy of E1, energy of E2, E3, and n, small n here, En, and so on, right? So we said that we will, instead of writing a wave function, the occupation number formalism of this picture is any quantum system. I just will count. The system can be in these states. How many particles are there in each eigenstate or each orbital, if you might. So this can be the s orbital of a hydrogen atom. This could be the p, and so on. So this is the slightly different way of. Maybe I should write it E sub j, just to avoid confusion. E sub j, a slightly different way of thinking about the states of a system. This is the occupation number state. And based on this, if we have bosons, which are phonons or photons, in fact, it goes quite a bit beyond that. I will have a brief discussion of that today. Then I have operators which are two operators. I define two operators with small b with a hat, let's say, just to remind ourselves it's an operator. And we go to orbit. An operator is defined for each orbital, and this is an annihilation operator for the jth orbital. Similarly, we have a creation operator, say for the ith orbital, would be like that. Okay? And for bosons, these operators satisfy a very a nice commutation relation, meaning if I take bj's and bi dagger minus bi dagger bj, that is equal to 1. So this is for bosons an intrinsic property. And if I take the same, if I take just annihilation operators, then they that's always 0 if we are not taking the mixed product of the operators. If I'm not creating and annihilating, it's always 0. Or if I create both, it's always 0. So these are the fundamental algebraic relations that are satisfied by these operators. Sorry, the dag is equal to 0. That's for bosons. Yes?
Is that each orbital has its own operator on each state?
Absolutely. Each of these states, each orbital has its own creation and annihilation operators. Yeah?
Several orbitals on one state.
Say that again?
Is there like several orbitals in one state?
Are there several orbitals?
Like spin up and spin down?
Yeah. So if I have spin up and spin down, I will split them and say that this is spin up and that's spin down. They're two different orbitals.
Two orbitals.
Yes.
But they're at the same state. So
They could be, oh, I see what you mean. There can be many orbitals that can have the same energy. Absolutely. The way I've sketched it is maybe misleading that they all have different energies. Not necessarily. They have different spins or different momentum, or the moment we apply it to a semiconductor today, you will see, how it works out. There'll be, the orbital indices here could be, for example, which site of a crystal are you sitting in? Which atom of a chain are you sitting in? Are you sitting here, here, here? It could be the site index. It could be, it all depends on what problem we are trying to solve. It could be the momentum index. It could be the spin index. So these orbitals are in any basis you choose, but you have to choose one basis. You choose either a spin basis or a momentum basis or a location basis. In that, as long as you're consistent that each of these are, say, I choose the E energy versus momentum, which we are going to do quite a bit today, the momentum basis, then the orbitals are indexed by k, which is the h bar k is the momentum of the particle. And so each momentum, so this state has a different k than that, than that, than that, and each of them have energies. For example, these two k's can have the same energy, and that's okay. You just have to keep an index of a basis set. I don't know whether this answers, but hopefully as I apply it today, it will become a little clearer. So I see. Okay. So that's for bosons. And I think you can see from here that for bosons, it really, you can create two bosons in two different orbitals, and it really does not matter which way you create it, meaning they commute. If I create one, you can see that I can take this to the right side, and it's saying that whether I create a boson in orbital j and then in I, the wave function will say the same if I create first in I and in j. The reverse process is the same. It doesn't flip its sign. But for fermions, this is quite different. And we define these operators again. So just to be clear, what were the actions of this? So if I take, I'll just write one relation here. I think I've repeated it a couple of times earlier. So if I take B sub I dagger and I act on this N1, N2, N, J, and so on. Let's call it Ni here, okay? So what will that give me? So it will raise the number of particles in the ith orbital, right, by 1, by exactly 1. And so that will give me a new state which has N2, Ni plus 1, and then everything else it doesn't touch. And then outside here you will get a Ni plus 1 as a normalization factor. And annihilation operators will reduce it by 1, but if any of this is 0 and you apply the annihilation operator where the operator index acts, it matches that orbital, it will give you the number 0, not another state, but it will annihilate into vacuum. There will be nothing left there. For fermions, we said we are going to use these two operators instead of B. The notation we are using is C, and again, these i's and j's are dummy indices, as you may easily see. C, J, dagger. So here we defined as a curly bracket, and curly bracket here meant the anticommutator. There's a plus sign instead of a minus sign. And I just want to kind of emphasize that this one sign change has such a dramatic effect on the physical properties of systems. This is rather amazing to me. I mean, most people find it very amazing. Just the sign change is responsible for this whole two different classes of materials with very different physical behavior, right? So the plus sign is what's called the anticommutator or antisymmetric commutator. And again, so here, if I take Ci and I take the same annihilation operator on two orbitals, and except now it does matter which one you create or annihilate first. In fact, it's okay. So you get 0 if I take just the annihilation operators. Here it's a mixture of annihilation and creation. If I take Ci dagger, Cj dagger, again the plus sign here. Equals 0. So this is saying that if I have two orbitals, orbital I and orbital j, and I try to put electrons in them, I first put an electron in I, and then I put an electron in j. That results in a certain state of the system, right? But if I do the reverse process, if I first put it in j and then in I get a minus of that. The state I get will be minus of the state. The wave function will flip sign. State is the same as the wave function. State of the occupation number state is the same as the wave function. The wave function will flip sign depending upon which state I fill first. It'll just flip sign. It won't change its mod square, but it'll flip its amplitude sign. And this is the nature of fermions. And this is why if I either put if I do this in the same orbital, you can see right away Ci dagger squared plus C, if I is equal to j, you get a 0. Right? And that essentially, because it has to flip its sign, it's come back to itself, and you get 2 times this. From here you get 2 times that is 0, so that is 0. And that means, and this is the this is the Pauli exclusion principle, that I can't put 2 particles in the same orbital now. Right? And this is guaranteed in this mathematical formulation. So you don't have to build it in, by hand. If you accept this mathematical formalism, it is built in from the get-go, from the beginning. So you don't. Okay. So physically, hopefully it's clear. This with the dagger, you're creating a particle, and with the and that's the destruction operator. Okay, we'll start applying it today. Let me start with a connection to the nature of fermions and bosons. So just a couple of comments about fermions and bosons. I also mentioned that particles that have, or rather, something called the spin statistics theorem in quantum field theory says that bosons must have an integer spin, right? Not half integer, but integer times h is the spin of all anything that is a boson will have a spin of Planck's constant times an integer. Integer could be 0, 1, 2, 3, 4. Fermions must have half integer spin, so half integer times h bar, so half integer spin. So could be cannot be 0. So could be plus minus half h bar, plus minus 3 half h bar, and so on. And these, if I have only one boson or one fermion, this is the algebra they are satisfying. But if I have many, if I have 10 to the in a solid semiconductor solid, metallic solid, I have lots and lots of electrons. And in fact, the crystal can vibrate, it can generate lots of phonons. So there can be quite a bit, very large numbers of electrons and phonons. And so, for example, the number of electrons is easily, in the order of the atomic density, right? 10 to the power 23 per centimeter cube. It's very large numbers, right? So one of the questions is, if I have these energies for both, electrons or for fermions or bosons, how, because of this restriction of fermions and no restriction of bosons, how do they distribute in energy? If and that's a very interesting question. And the question is posed in this manner. Well, let's say I have a collection of fermions, and this is in. I'm going to summarize it. I don't think in this course we have time to derive this relation. And this thing is in equilibrium, and we'll divide this. Okay, equilibrium with a heat bath or something that has a temperature T. So you can see this is an element of thermodynamics. There is a system of either fermions or bosons. Okay. And this collection of fermions, it could be electrons in a semiconductor solid or a metal, is in equilibrium with a system that has a temperature T. And temperature is not a quantum mechanical concept. Temperature is a thermodynamic concept. So this is a thermodynamic idea where thermodynamics essentially here in the sense that what it means is I kind of crudely speaking, it is a classical concept. And classical thermodynamics with it's a measure obviously of the entropy or the energy of the system, the temperature. Okay? So if this system of fermions or bosons is in equilibrium with a heat bath, I mean that's the word used here, and this heat bath is able to supply or to source or sink any amount of energy from this system, right? So it can exchange energy, it can take away energy. If this is way out of, it has too much excess energy than this one, it can give it energy, it can heat it up if it's cold, and so on. It wants to bring it to equilibrium, right? So that's the picture. And I've written this up, by the way, in one of the chapters in the handout on statistical mechanics. I mean, the picture to have is a reservoir, a heat bath, and here's your Fermi system or your Bose system, Bose-Einstein system of energies, and this is in equilibrium. Okay? So if you now ask this question and you go forward and say, for bosons, I use this bosonic operator algebra and say that I have this set of systems, and if I have particles of bosons that can distribute in energy, how do they distribute, right? So this temperature here will, the distribution of these particles are given by what you do is you find the probabilities. So there's the one of the most important results of quantum stat mech is the probability of finding a particle in an energy orbital with energy E1 or E2. The ratio of that is given by the Boltzmann distribution. E to the power minus beta here is 1 over kt, k being the Boltzmann constant, kb, right? Now, Kb or Boltzmann constant is really at least till today, it's not possible, has not proven possible to be derived from quantum mechanics. It's a statistical thermodynamics thermodynamic concept. So if you have two states with or one state with energy E1 and another with energy E2, the ratios of occupation, or probabilities of those are given by this sort of thing. In StatMech, it comes about from this equipartition of energy and et cetera, et cetera. So anyway, so what I wanted to get to is if this fermionic or bosonic system is in equilibrium with a thermal bath, what we can ask is when it's in equilibrium, the number of particles I'm going to just sketch an example here, and we'll come back to this again a little later. So let's say these orbitals we are talking about are different k states or momentum states, and we'll derive this in a later part of the class today. Okay? And this is in equilibrium with these are electrons. These are electronic energies or energies of electrons, and maybe this is h square, k square by twice of the mass of the electron. And they are in equilibrium, and these states are now in equilibrium with the underlying crystal, atoms and the vibrations, and that solid is sitting on some surface which is at room temperature, or you cool it down or something like that. So that's the heat bath we're talking about. It's sitting on some surface, and that has certain temperature, and the concept of this heat or the temperature is, let's say, the surface it's sitting on. That's the temperature we're talking about. Now, so these energies now we are going to label as E sub k, and that's the formula for E sub k. And based on this, we can start asking the question, and this is what I wanted to get to today. If I look at any state k here, labeled by k, it has a certain energy, and I know that for that state there are these creation and annihilation operators. C sub k is the annihilation operator, ck dagger is the creation operator, right? For that state, for that orbital, right? And whenever a system is in equilibrium, the number of particles is in thermal equilibrium with something else. The number of particles is fluctuating. It's not constant. It can be basically why? Because this can be giving particle away to the heat bath, or it could be the particle will be coming back from the heat bath. It's essentially it could be dumping energy or gaining energy. But that's the meaning of equilibrium. Equilibrium doesn't mean that the number is not changing in time. It's saying that statistically there is a process where it's dumping energy and it's gaining energy, but the net energy gain and loss is zero. And it's a Sassley average. So over time, if I take this number, C dagger C is the occupation number of that state. That's the physical meaning of that, right? The occupation number of that state. Now, the occupation number at any given point of time can be either 0 or 1 if it's a fermion. So there's no other option. It can be either 0 or 1, right? Ck dagger Ck will be either 0 or 1. And on the other hand, if I take this measurement by some means with an infinitely precise in time meter that's tracking whether there's electron there or not, and I integrate it over a window of time, this is a time average. If I take a time average of it, right, I'll get a number between 0 and 1 for fermions, right? And that number is what was derived by Fermi and Dirac, and that number is the Fermi-Dirac distribution. So that's the meaning of this thing. So Fermi-Dirac distribution is given for that energy orbital, right? And the expression is e to the power energy of that orbital minus a Fermi energy, or sometimes we'll refer to as a chemical potential, divided by Boltzmann constant times temperature plus 1. So this is average, in that sense I mentioned just now. And to derive it thermodynamically, you kind of, it's actually pretty straightforward. To find the occupation number, average occupation number, you take, if I have 0 and its probability or the weight, Boltzmann weight is e to the power its energy, plus if I have 1, occupation number 1, it's e to the power beta, this sort of thing, and divide by what's called the partition function, and you get this result in one step. Yeah. So that's for fermions. I'm not, I know I've not derived it, but I hope at least there's some connection to what we are discussing here. So the physical meaning of how fermions are distributed and what is the connection to these operators we introduced earlier. So, yeah. And because these are fermions, there is no 2. It's either 1 particle or 0 particle or 1 particle. There is no 2. And this sum over states, all possible configurations of the state ends with only 2 terms. There's no more. So, yeah. So this is a Fermi Dirac distribution. On the other hand, if you are looking at bosons, right? If you have phonons or photons or bosons will satisfy for bosons you can have any number of particles. There's no restriction. So you can have 0 or 1 or 2, 3 all the way to infinity. So you get a sum which looks like that, and when you sum it all over, you get a result that looks very close to this, but it's not quite that. So the average in the thermodynamic sense I mentioned. So bosons, I will not use K. This is again a notation. Small k we are going to reserve for fermions or electrons primarily for us, and for bosons we are going to use Q. Small q. That's just the wave vector. And we'll see, for phonons or photons, the energy versus Q, let's call it H bar omega Q. So there are many Q states here, and the orbitals effectively are indexed by different Qs, and the occupation numbers average is given by the Bose-Einstein distribution now, for E sub q, energy of that orbital, and e to the power E sub q minus, again, okay, you know what, I'm going to, EF is Fermi energy, and I'm going to label it at this point as a chemical potential just to maintain uniformity between both. EQ minus a chemical potential here divided by the same Boltzmann constant times temperature minus 1. So you get the minus here instead of plus. Okay. At some point of time, I mean, the chemical potential can have 2 components. There's the electrical component and there's a chemical component. So in semiconductor physics or electronics, there is a difference between the chemical potential and what we call as a Fermi level. So, but if for example, you can calculate exactly how the chemical potential changes with the Fermi level. Basically, both of them are a measure of number of particles. How many particles there are, either fermions, how many fermions there are, how many bosons there are. More is the number of electrons you have in the system. More is the chemical potential. So yeah, there's a question.
So for that value to the occupation,
yeah.
Is that the same occupation number as the Fermi Dirac, or just in a different notation?
Ask that again.
Is that the same occupation number as in, occupation state as in the Fermi Dirac distribution? Or you just?
You mean this one?
Yeah. The Q, is that the same as K?
Oh, yeah. So remember this Q and the K. Okay, thanks for this question. So the Q and the K are, these are, at this point of time, these are indices of the orbitals. These are just you can think of as a dummy index of how you are counting the orbitals. Okay, I could be counting the orbitals, I think she was asking earlier, by K. I could be counting the orbitals by which site on a crystal is it sitting in space. I could be counting in any ways. Right? As long as you know what is the energy of that orbital, Fermi Dirac distribution doesn't care which basis you are talking about. It just wants to know what is the energy. Does that make sense? And then it could be E sub k. You can, K and Q, the way I've labeled it is Q and K are 2 pi by wavelength of this particle. And in here, it's 2 pi by, so it's 2 pi by wavelength of, say, a phonon here. And it's 2 pi by the wavelength of an electron here. Okay? But in the expression for BoseEinstein distribution or Fermi Dirac distribution, this energy term really does not care what orbital you have chosen, what's your basis, as long as you know what is the energy of that. That's all it cares about. So that's what I want.
Okay, so it doesn't have to be in a crystal.
No. It can be it could be a bunch of electrons in vacuum, for example. Absolutely, yeah. It doesn't have to be. Okay, so now based on this, these two distributions, and I mean this sign can really be tracked down to this sign, as we had just mentioned. The plus versus minus. That's where you can track it down to, plus versus minus. And because of this, I think that if I take these two distributions and I make a plot of it, so the Fermi Dirac distribution clearly has 1 over 1 plus something, which is exponential of something real. It's always positive, so it's always equal to or less than 1, right? That much you can see. Whereas Bose-Einstein distribution has 1 over something minus 1, so this thing can blow up. It can go to very high values, the Bose-Einstein distribution. So when you make a plot of it, let's first look at very high energies. At very high energies, or very high energies of the orbitals, this becomes, as you can see, this is much larger than 1 when the EK is much larger than the chemical potential. So the exponential, you can bring it to the numerator, and it just becomes e to the power minus EK minus mu over KT, right? And similarly here, you can see at very high energies, you get exactly the same expression. Right? Exactly the same expression. There's no difference between the two, EQ minus mu over KBT. Okay? And classically, if you are talking about particles like electrons, they can, this is the energy. So, except for the chemical potential, you can see it will be half mv squared over KBT. And then there's a chemical potential, which is a constant term. So this is called the Maxwellian distribution. This was classical mechanics. If you had a collection of particles before quantum came along, people already knew that there was a distribution like this to explain the motion of gases and collisions of molecules and atoms and all that, and how they move, how do they distribute energy. This is called the Maxwellian distribution of energies. You can see it's a Gaussian in the velocity of particles. This is classical mechanics here. But this little sign change and fermions and bosons make the difference as you get closer, lower in energy, and then they really split in a big way as you go to very, chemical potential and lower. Was there a question? Yeah.
So part of this seems like it's based on statistics and having enough actual population of
Yes.
fermions. So where does it break down to the point where you don't have enough, let's say, electrons?
Very good question. Yeah. If I have only one electron, it completely breaks down. You can't apply this distribution function, because actually when you have only one electron, you don't even get to apply this, right? You don't have a nature of, Pauli exclusion doesn't kick in yet because you don't have two yet, So if you are asking quantitatively how many electrons do I need, is that something you're asking? Or
In the extended solid, maybe like a quantum well or quantum wire?
Yeah. So, most, it's actually, let's see. So if I have, mathematically at least, I can tell you this sort of depends on, n factorial, is, what was that? The Stirling approximation, right? That gives you the estimate. What is it? I keep forgetting. N factorial is, the natural log of n factorial is n log n, or something like that, right?
Minus n.
Sorry?
There's a minus n afterwards.
Oh, minus n. Yeah, so if you take this and you say, here's the approximation, and you calculate for what number n it fails, that's roughly the number where this will fail. So that's where it comes from mathematically. You can calculate it for an integer. I forget. I mean, it's actually like 10 to the power some large number, I think. Not 23, but even at 10 to the power 7 per centimeter in a nanotube, for example, this is good. Fermi Dirac is already operational. So, but I think you can calculate it based on this Stirling thing. But what I physically wanted to say was, this. You can see that near the chemical potential and below it, you see this very vast difference between the two types of particles. If it's bosons, it would do that, versus fermions would go to 1. And in terms of this particle number picture, let me erase this. Particle number picture, you can see that, let's say I have labeled my particle numbers from 0, 1, 2, 3, and so on. For fermions, the number of particles will, at very, very low temperatures, at say 0 Kelvin, close to 0 Kelvin, you can see at 0 Kelvin this is a unit step function, right? So if you put T is equal to 0, so this becomes, if energy is larger than mu, then this becomes plus infinity, you go to 0. If energy is slightly lower than mu, this becomes e to the power minus infinity, right? So you get 1, but e to the minus infinity is 0, so you get 1 over 1 is 1. So you get a unit step at 0 Kelvin. I think this is something you probably have seen many times, and as you heat up the system, it starts broadening, and this broadening is few kTs. So if I were at 0 Kelvin and I try to write the state of my system, you can see that the state of the system will be very interesting for fermions. It will be 1, 1. It will be filled all the way to the energy of the orbital, which chemical potential is mu, which is equal to the mu, right, which is the chemical potential. And then above it, it will be 0, 0, and so on. Right? This is the state of the system in the occupation number picture. Does that make sense? I mean, right? And you can even make this is not necessary, but you can make a plot of it, which is, this is the plot we're looking at. So your, occupation number, CK dagger, CK is equal to 1 for all states. It's 1, 1, 1 for all states below mu, and it's 0 above it. So that's the physical meaning of this. And for bosons, on the other hand, you can blow up, and it can go up to very high values because there's no restriction, and that leads to condensation and other phenomena like that. Okay. And really, this is the reason why there's a difference. As I mentioned earlier, the reason people kind of were forced to looking at this multi-particle nature and then discovered the difference between fermions and bosons was the helium atom spectra, which has just 2 electrons, and it couldn't explain it with a single particle picture. And then, the moment this was realized, that right away explained why for example, the existence of the periodic table in the first place, right? Why are there hydrogen and helium? Why are there, as you add electrons, why do they occupy different states with different energies, right? Why are they not all at the same energy? The existence of the periodic table, entire chemistry, and all that stuff is tied to this, and it's kind of interesting in that sense. Another very interesting fact is, which we will encounter later when we talk about Cooper pairs or superconductors, you can have composite particles. You can have composite particles. I can have, for example, I can have 2 fermions. 2 fermions can combine to give you an integer spin. 2 half integers can sum up to give you an integer spin. So that composite object can become a boson. 2 fermion object can become a boson. It could be an electron and a proton or something like that. Similarly, rather, the other way is not possible, as you can see. You cannot combine 2 bosons to get a fermion, right? Because they're already integer, right? So can't get half integer by summing integers, but you can combine fermions to get bosons. A very good example, or you can combine a fermion, 2 fermions with a boson to get another boson. A good example of that is an exciton, where you have an electron and a hole and a photon. They combine together, and an exciton is a bosonic object. You can make it condense. You can have many, many excitons in one state. So you can beat the Fermi distribution that way. Similarly, another really classic example is the Cooper pair, which leads to superconductivity, where 2 electrons of opposite spin and 1 phonon, which is a boson, combine to form the Cooper pair. So we're going to look into those things in this class. Okay. I think probably the most striking example of the difference of fermions and bosons is, so you have helium atoms, and you have two isotopes of helium, helium-4 and helium-3. This is actually a very good example because helium-4, the difference is helium-4 has one extra neutron in the nucleus. It's one extra neutron. It's an isotope. And so helium has 2 electrons, 2 protons, and 2 neutrons. Is that correct? Yeah, that's that. Helium-4. 2 protons plus 2 neutrons gives you atomic mass of 4. Whereas helium-3 has 2 electrons, 2 protons, and 1 neutron. So that gives you 3. Now you can see that proton, neutron, and electron all are fermions, but you have an integer number. Right? Sum them, you get an integer spin. So this, at low temperature, it becomes what you call is a superfluid. It flows without any viscosity, superfluid. Whereas helium-3 is a fermion because it has an odd number of half-integer spins. Right? So you sum them, you still are a fermion. So it never condenses. It doesn't form a superfluid. For example, helium-3, because this whole object is a fermion, the composite object. And I think, on the other hand, as you know, fermions can pull together and form effectively a Cooper pair, just kind of going to another. Yeah. The condensation of helium-3 was predicted to happen at extremely low temperatures when it becomes something like a electronic superconductor. And this was discovered here at Cornell a few years, in 1980s or 70s, I forget, and it's a big result. But okay, so this is a slight off track, but I'm saying that helium-3 and helium-4, if you go to those low temperatures, I think Herb Kromer's book says it very nicely, that they behave like oil and water. They don't mix. They're the same atom, but just because one is a fermionic nature, the other is a bosonic nature, they completely phase separate, and then you can see the difference between these two particles. This is the essence of this fermions versus bosons. Same atom. So, yeah. Okay, good. So as far as this course goes, we'll have this idea. When I said there's a thermal bath or a heat bath to which things are connected, this is a generic concept. In general, we will be connected to electrodes or metal electrodes or contacts, sources, drains, gates, all that sort of thing. Those contacts are our heat baths effectively, and those contacts will have their chemical potential or Fermi levels, and we will be able to move, primarily in a semiconductor, we will be able to move this what we are calling as the mu, or the chemical potential of fermions. And that is the most powerful sort of control tool that makes semiconductors so useful. You can actually move the Fermi level or the chemical potential of a semiconductor by having two contacts. One is at a high Fermi level than the other, and this thing will try to inject electrons into this, and the other will try to take it away. And so that's how current will flow, because of this imbalance. And then that's how we're going to look at transport phenomena. So at low temperatures, if I have two electrodes with different Fermi levels, you can find out over what window will electrons flow inside the semiconductor. And so this is just trying to say that most of the useful things we do with semiconductors is tied to this function here, the Fermi Dirac distribution. We are basically tweaking it with a gate voltage or a drain voltage, or tweaking it to emit light or do something like that. So, but we are always tweaking this. That's what we are always tweaking in a semiconductor device, for example. A very good example is a transistor where we are switching it on and off. So Fermi Dirac distribution, so if your occupation number is very high, you will get a very high current. If your occupation number is very low, you will get a very low current. So your on and off, or ones and zeros, are also related to that distribution function there, the Fermi Dirac distribution. And this is something we're going to, I think you will do this in reasonable detail. Transistor, you'll be able to model it. And just to be, I want to emphasize that all of this is related to the Fermi Dirac, and you will be evaluating its integrals, perhaps using Mathematica MATLAB or something like that, to sum over all the particles that carry current here. So This is just the Fermi-Dirac integral. But if you look at a transistor, the current looks the same. It's just a map of this. Okay, so I will, I have a few things. I'll probably kind of skip this part here and start talking a little bit about building up the. Just a sec, yeah. Yeah, we haven't yet started talking about band structure and the EK diagram and what orbitals do we choose, as we discussed a little bit earlier. That's something I want to come to right now. I want to start building, the idea of what are the allowed energies for electrons, what are the allowed energies for phonons, and then when transport occurs, how do we visualize the exchange of energies between them and so on. That's something we want to talk about right now. So let's. I'll just blank this for now. Let's discuss that. So what I'll do is start with what we can call as a toy model, which will explain, or which will capture most of these concepts that we mentioned today. Okay? So here's our goal. First of all, earlier we have already written down an expression for the current, right? So Q over mass. If you find the wave functions, you take, minus psi. I just write down p psi star, right? If you know the wave function of a quantum mechanical particle, you can write down the current of that particle, and that wave function could be of any orbital k, So that's something we had written earlier. What are we doing now? We are trying to find out which orbitals are occupied and by how many particles. That's what we are trying to find out. And we find that it's very different if it's a boson or a fermion. The distributions are different, and these are the average, equilibrium values of occupation. Right? So the current carried by a state k or orbital k is given by that expression we had derived earlier. But whether this current will actually be carried or not depends on whether there's a particle there to carry it or not. And these are the occupation functions that tell you whether they are there or not to carry it. So you must multiply this with the occupation function of that state. Does that make sense? To say whether, it can carry this much current, but whether it's carrying or not is dependent on how much of it is occupied. In other words, you can think of this effectively as your electron density, and this is your velocity, if you may, somewhat like that, number of particles times how fast they're moving, something like that, or flux. Flux. So, okay. So, and so if I come up with a band structure with many k's, you already have an expression to find the current carried by that k, but we also need to know, what is, if it's a fermion, what is this thing, right? And that's what we just talked about in the Fermi Dirac distribution. Okay, so now what I want to do is say what is this energy distribution and how do you find it? And that's actually related to what situation the particles find them in, what sort of potential. You solve the Schrodinger equation for that, right? And we have already talked about that in a particle in a box picture, but I want to build towards a solid. We want to look at a solid, a crystalline solid, for example. And I think so I just want to get a show of hands. How many of you have seen where band gaps come from and band structure? So some of you have kind of not. Okay, so okay, I'll try to build that up now. Okay, so what are the energies allowed for an electron if it's completely free not in a solid? Then we know that we have already done the free electron problem. It's 8 square, k square by twice mass of the electron, right? Those are the energies allowed for a free electron, right? We have done that. Now, if it's not completely free, if you place it in a ring, for example, or a length, then we know that this will become discrete, right? If the length of a ring is L, then the separation here will be 2 pi over L. But the energy will still, the expression for the energy still stays the same. Right? It's just, the k's become discrete because, you have to satisfy the wave fitting into that little circumference here. It just become discrete, right? But it still goes to kind of very large values. And there's no such concept as what is a band gap. There's no such gap. But if you look very finely here, there is a gap. You don't have those two energies, any energies allowed between those two. So it's that's because you are going between this and the next number of half-wave vectors. So there's that little thing, right? But things change obviously very drastically if I put this electron in a periodic crystal. Okay? So let's look at that first. And I'll first state the result, and then we'll. So a periodic crystal you can think of as a chain of atoms, right? A linear chain of atoms. And we can start with one dimension, and we build it up towards 3D and all that. Okay? And what I want us to picture it as is not an infinite from minus infinity to plus infinity, but as a small section of maybe a periodically arranged layer of atoms where it's closed on itself. It's a ring, let's say. It's a very long ring, for example. Right? It's very long, then if you're looking at a small window, it looks like a straight line here, right? So we can think of it that way. This is just for mathematical simplicity, to have a finite number of atoms and have integrals converge and all that sort of thing. So yeah, it doesn't lose any physics. So that's, just want to say that. So I have a chain of atoms, and an electron now. We want to launch it and then see what's the transport of this electron, right? How does it look? What are the energies allowed if you have a chain of atoms like that? I think you know that because of these atoms there are these potentials, right? That the electron will see. It's a periodic potential, right? So if you can think of it almost classically that there's a bumpy road, very deep bumps, because the electrons at the core of the electron of the atom, or the center point of the atom, the potential, it's a very deep potential well for it, right? If you think of it in the Coulomb interaction sort of picture, right? So because of this, and this is your periodic potential, V of x plus A is the lattice constant, right, is equal to V of x. This is your new potential now. And V of x has some shape. It's maybe 1 over r, some shape here. And you're in a standard way of solving Schrodinger equation, you can go back and solve this equation now plus this periodic. Let's write it as PER as the periodic potential, right? Is E psi of x, right? When you solve it, so what you'll find is that not all energies are allowed. In fact, physically, when the electron wavelength becomes commensurate with the lattice constant, you can think of it from a very classical picture that electron is going or you can think of it as a wave that's going through a grating. If the wavelength becomes the same length as the grating, there is very strong interference and diffraction, right? Does that make sense? If it's very far off from the grating, if the wavelength is very mismatched with the grating, it doesn't see the grating, right? The wave doesn't interfere. Whereas if the wavelength becomes equal to the grating, then there is strong interference and diffraction, right? Does that make sense? That's an intuitive wave concept, right? And then so you know that in this free particle picture, for wavelengths is 2 pi by the wavelength, right? For wavelengths that are of the order of the lattice constant, not the order, will have a precise relation. If 2 times, let's say if the wavelength becomes like that, so wavelength is wavelength is 2a. I think that's what you have destructive interference. If you have the wavelength is 2 times a, then your k becomes pi over a, and at those conditions the electron actually cannot propagate through the crystal. It's evanescent. It diffracts or forms standing waves. It cannot propagate anymore. And if you're far off from there, it kind of, it's affected by the atoms, but it doesn't see it as much. But it sees the crystal most severely when the wavelength is exactly equal to 2 times a. So let's just put it this way. So you have, as a result, minus pi over a And what happens is at low energies, the electron energies look very similar to the free electron, but as you come to this edge, it actually will look something like this. So it okay. And there is a certain range of energies that become gapped. Those are not allowed anymore. Those electrons with these energies will not be allowed to move through the crystal anymore. So that's your band. These are energy gaps, right? I'm just summarizing the results. I'm not deriving it at this point. And I think physically it is very deeply related to this wave interference. If you have done courses on X-ray diffraction and other things, this is Bragg's law for electrons. It's exactly the same thing. There's no difference. Now what I wanted to do was a slightly different approach to this, but let me summarize the results. This breakthrough kind of came with Bloch, Felix Bloch, who said that to solve the Schrödinger equation in a periodic potential, you can write your wave function as still a free electron wave function, which is e to the pi kx, but modulated by another function which is periodic with the lattice, with the lattice constant. So if you didn't have this, it would be a free electron. But Bloch said that if you do this and you insert it here, you can find the solutions. And actually, indeed, when you insert it here, you can find you have to solve an energy eigenvalue problem, and you get that there will be gaps, there will be all these curvatures and all that sort of thing. These are the allowed energies for the electron. The K's are still separated by 2 pi over L, where L is the macroscopic length, not the atomic lattice constant, but the that length, all the atoms. Could be a micron, could be a centimeter, or if you have a 8-inch wafer, it's the 8 inches. So that's it. So this separation is extremely small, but it's still discrete. So that's just what I want to say. And there are exactly as many these points here as there are atoms in the crystal. It's exactly the same. If I have n atoms in the crystal, big N, then there are, if you count all of these, you have big N points here. Okay, and because each of these states, if it's a fermion, if its electrons can hold an up and down spin, so this would be called a band, and it can hold 2n electrons. Each state can hold an up spin and a down spin. They are, for quantum mechanical considerations, they are different orbitals, up and down spin. So at any energy, you can see you have a degeneracy of 2. You have 2 states, and in fact there can be 4 electrons at that energy. It can be up or down, it can be up or down. But they are very distinct. They are distinguishable. Do you see that? I mean, they are all distinguishable because this thing is going to the right, and it has downspin, and this thing is going to the right, but it has upspin. So they're distinguishable. You can do a measurement and distinguish between them, right? And similarly here, there's one going to the left and right, but they're different spins, but these are going that way, right? So they're so that's the so you can have multiple orbitals. So you have, what I'm trying to say is you have 4 orbitals here with minus k, plus k. I can write it as minus k comma spin up, minus k comma spin down, and plus k comma spin up, and plus k comma spin down. So there are 4 orbitals really, right? And it just so happens that all of them have the same energy here in this situation. So, okay. Right? Okay, so right, so a few more things I wanted to summarize, and then we will actually start writing, deriving of some forms of it. The thing that fact it curves around is very important. You can see it's actually very difficult for me to summarize all of solid state physics in a few minutes, but because we are going to use it multiple times, hopefully it will, if you haven't seen it, and you can discuss more, but I will try to emphasize some of this concept there. So So the allowed energies went from like a free electron picture, which was a parabola, to these gapped regions with curvatures. And these curvatures, are, how much it curves is what's called the effective mass of that band at that point in K. So the free electron was something like that, and it had a parabola. By definition, has the same curvature everywhere, right? The same curvature everywhere. But if I take this line and I make it bend like that, this has different curvature than the parabola. So my energy mass here, the way we think about it is we say that it has a different mass now, just to capture that curvature, right? And that's the meaning of this effective mass. You can see it's a mathematical concept, right? It's just saying that I want to capture the motion. If I'm looking at the, if I want to write it as h squared k squared by 2m, or its kinetic energy as half mv squared, it's the same as half mv squared. H bar k is the momentum, right? Then the mass effect, it looks like it's a little heavier now, right? If it's curving this way, and or lighter, depending upon how it goes, right? So the curvature near the band edges is a measure of the effective mass, and very close to here, you can write it as a minimum here could be an EC plus an h square k square by twice the effective mass of that band C. C could be, this is the label of my band C, let's say. So this could be, for example, in certain solids, this can be my conduction band, this can be my valence band. And so the valence band might look like that, conduction band might look like that. If I want to call it the conduction band and valence band, and this as my energy band gap, then maybe I can ask you this question: how many electrons are there per atomic site in this solid? So what should I ensure if this is going to be my conduction band and that's my valence band? Yeah. One electron per atom. We also have spin. Yeah, right. Okay, good. So you see, so there are n sites here, right? And each of them can hold 2 electrons. And when I say a valence band in semiconductor parlance, that means it's filled, completely filled. Your CK, dagger CK is 1 for all of them, so, or occupied. So as a result, so you can see that I have to put in 2n electrons to fill this thing, right? And start from here, put 2 more, and then fill it up, and then when you are at 2n electrons, you're out of electrons now, right? Meaning if you have filled it up till here, this band is completely filled, this band is completely empty, and you have a gap, so that's a semiconductor. Right? That's a semiconductor. If I had 1 electron per atom, then you can see I will run out of electrons somewhere here, right? What is that? What electronic property? Yeah. So that's a metal, right? That's a metal. Why? Because you see there is no energy gap between the highest energy occupied here, meaning smallest voltage I apply, smallest perturbation I apply, this electron can go here and conduct. It doesn't, it's a very good conductor. Right? It's a very good conductor. So that's a metal. A semiconductor is when there's a gap at the Fermi surface, at the Fermi level. So you have to do something to make it conduct. Otherwise, it's an insulator. Right? So you have to probably dope it. You put some dopants here and fill this conduction band with electrons, or you put a gate on it and you pull the Fermi level up electrostatically and you fill it with electrons, or do something like that to make it conduct. If not, if at low temperature, or if you heat it up, these things can jump over here and conduct. You leave some holes and conduct, right? So that's a semiconductor. Right? Semiconductor, metal, and so you have semi-metals, all other kinds of phases of electronic phases of matter, now topological insulators. We'll discuss those things. But at least this is, at least, I think some of you have probably seen it quantitatively in great detail, but, let's look at this picture from a slightly different angle now. So, right? Okay, so we are going to track obviously transport of it, but I want to develop this using this occupation number formalism, give you the basis of what we're going to cover. Okay, so instead of solving the block equation, or Schrodinger equation with block functions, because we have developed all these ideas of creation and annihilation operators, we can write the electronic structure and the phonon structure in a very slightly different way. It's somewhat modern way of looking at it. And let me outline that. So now I have atoms, okay, and it's not very modern, really. Those of you who have seen a tight binding model, we're going to kind of use that a little bit now. But another way to look at it of what are the allowed energies, what are the allowed EK diagrams or for the electron is instead of starting with a free electron picture where the electron was going along, and then we say that because of interference and diffraction it gets gaps, right? We started from a free electron and said, going to get gaps. Right? There's a whole different approach of this, and this will also give us a EK diagram again. And if we do it right, it'll give us the same, for example, right? And I just want to emphasize, once you know your EK diagram, to me, your transport problem is kind of solved, because each of these points you can apply, you know your wave functions, and you apply your operator and find the current due to that. Find your Fermi Dirac distribution or Bose-Einstein, depending upon what particles you're looking at. Sum them all over, you get your current, right? So that's the prototype transport problem. You find all the quantum states, JK, find their currents, I think I erased it, and then sum them all and you get your net current. It could be a heat current, spin current, charge, whatever be it. But we are going to look at the reason I'm building this up with the operator formalism is all this works beautifully as long as you're in the single particle framework. The moment you have correlations between electron interaction, this picture kind of starts failing. So we are building up a little more powerful formalism to handle those things. Okay, so here's the picture. The other end of looking at the same problem is I have electron that's I have arranged atoms in a periodic crystal, okay, with a lattice constant A. It's the same problem, really. Right? But each atom came with an electron that was bound to it tightly. It was bound to it, like a hydrogen atom, let's say. So there's an electron that came bound to this atom. And I have brought all these atoms from far apart, and I've built this crystal, arranged them in a periodic lattice now. Right? So if the electron was bound to this atom, we are going to, I'm going to simplify this a great deal. This has a much more rigorous basis, but I'm going to say that if the electron was bound to that atom, it had an energy E0. Could be the ground state of the hydrogen atom, for example, or the outer valence state of silicon atom, for example, or carbon for nanotubes, whatever be it, right? It had an energy E0 for an electron to sit on this atom and be completely unaware of everything around it, all the other atoms, right? So that's. But now that I have put it in this situation, the one thing about electrons is they really don't like to be confined. It costs a lot of energy to confine them. Why? Because if you want to confine them in small dimensions, you have to have very short wavelengths. And short wavelength, means high K, means high energy. That's simple picture, of why quantum confinement costs energy. Right? So the electrons will not want to sit here. They will try to hop to the nearest sites. They want to spread out. And why? Because they'll lower the energy that way. Right? They're going to lower the energy of electrons and the whole system actually that way. Right? So let's say if it hops from this site, let's label this as site n, and this as n plus 1, and this as n minus 1, and then it's a periodic. It goes on. It's periodic. So if it hops to that site, let's say it lowers its energy by minus T0. Maybe a few millielectron volts or something like that. So that's if it hops from site n to n plus 1 or n minus 1. It can obviously also hop to n plus 2, n plus 3. It's not nearest neighbor, and that's okay. We're just going to keep it simple at this point. Just keep it this way. Okay? So now you can actually write this picture. What we want to find out now is, remember, so what I want to find to solve my transport problem is I want to find out my EK diagram. Right? What are the allowed energies and Ks of the system? Because once I do that, I've told you there's a prescription. Now you just find each of these currents and sum them, right? So you're done, right? But I want to find my EK, right? So to find my EK, how will I write this physical picture? That if it sits here, its energy is E0, right? If it hops, its energy is lowered by minus T naught, right? So I write the total energy of the system. And total energy of a system is what we call as the Hamiltonian of the system, right? The Hamiltonian of the system is equal to, let's just look at site n, just site n, right? So what should I write? If it's sitting at site n, its energy is E naught, right? But mathematically, I have developed this idea now, right? That how do I ensure that there's a particle sitting at site n? Right? So I can write it in terms of my operators, right? So, and how many particles are sitting here at site n? I can say that I write it in terms of operators A sub n. A sub n is a destruction operator at site n, and A sub n dagger is the creation operator at site n. And this combination is the occupation number, right? How many are sitting at that site, right? A n dagger, A dagger. Does that make sense? Okay. Okay. Simple, okay. So that's my first term for site n, which is the on-site energy, and this is telling you how many are sitting on that site, right? Right, the total number of particles sitting there. And for fermions, it can be either 0 or 1. It cannot be anything else. If it were bosonic particles, it can be anything, right? But I'm using, sorry, I think I maybe have confused you. I thought we decided we are going to use small c for fermions, so let's just use that, c for fermions, right? Okay, yeah. Okay, so now, so that's the on-site. Now you can probably help me to write this process. You can see the creation annihilation will help you to write it right away. So if it, remember we're writing the Hamiltonian, so it's going to lower its energy, right? So I got minus T naught. And then what combination of operators will give me this? So to have a particle or an electron hop from here to there, I must first annihilate it here, right? I must annihilate it here and create it there, right? So I must have a combination of operators where I am annihilating at site n and I'm creating at site n plus 1, right? So that's your operator method of writing down the hopping term from one site to the next. Right? Is that clear? So just, it should be simple at least. Again, what's the next one? What's the left hop? Again, minus T naught, right? And Cn. And then what do I write here? Right, so now it's labeled by n minus 1, and then there's a dagger here. So that is the energy of these three processes here, that we wrote here, right? But then you know that this site is not unique at all, right? This site is equivalent to every other site, right? So your total Hamiltonian is a sum over all sites n, right? So that's the total Hamiltonian of the system. Right? And it's now written completely in terms of this occupation number or creation destruction operators now. Again, I want to emphasize that for single particle band structure, you really don't need to do this. You really don't need to do this. It's an exercise, but it will make some things very clear. I just wanted to kind of emphasize that. But the moment I am able to put two electrons or multi-particle effects, there is no escaping it. This is what you need to do. So we'll look at Hubbard model a little bit later. And you'll see it leads to some very interesting consequences of on-site, repulsion and all that sort of thing. And what I wanted to also say that this is all, this terms we wrote is just for the electron. This is the electron Hamiltonian. Right? This is the electron Hamiltonian. And I'll write it in that way. This is just the electron Hamiltonian. And in the, actually Thursday, tomorrow, we'll see you can diagonalize this and you will get the band structure, EK diagram. You will get it from here. For that, you will have to transform from on-site to K-space and all. We're going to do that next time. But what I wanted to say is, in this picture, you can start adding in non-electronic effects, which are very important in most materials. Okay? So just want to, I'm not solving this right now. What I want to say is, this we will show tomorrow is equal to a sum over small k's, where k is the electron momentum, okay, times E0 minus 2 times T naught cosine of Ka times. Now you have your, I don't know why I like the A, so okay, Ck dagger Ck. we're going to see this next tomorrow. So here's the energy dispersion in K space, not in, in site space, but in K space, and that's your effective band structure. And now you have your creation annihilation operators in K space. We're going to show this tomorrow. It's a little bit of work, but it's not very hard. Yeah. 2T0 cosine of Ka. Cosine, yeah. So because of the two nearest neighbors, you get a cosine factor, and the band will look like a. So there'll be a E naught, and then it will, look something like that. The band will bend, and you form the band because of that. Okay, so because of a single orbital, and then these will be transformed into K space, and you get the occupation and creation annihilation of the K state instead of an on-site state. It's a conversion from real space to K space. So we're going to see that tomorrow. But what I want to end with today, just give me a couple of minutes, is in the same problem, what we can do is set up a bosonic system. And what is a bosonic system here? The lattice can start vibrating if I heat it, right? These atoms can start moving, oscillating, right? And this is classically imaged as a mass spring system. And the atoms, and this is not, we're not talking about electrons, we're talking about the atom, the mass of the, basically the protons and the neutrons. Right? And that it starts vibrating, right? As the electron moves, as it starts to hop, maybe the electron collides with the nucleus and it sets off vibrations in the, right? And those are phonons, right? In the same linear chain, I can set up the phonons and say that, well, there's a mass spring system, and the phonon Hamiltonian classically looks like this. I just will outline it. We'll do this in greater detail in the next class tomorrow. Yeah. Let's see. Here I have mass of the atom, not of the electron, but of the atom. Right? And how fast is it moving is xn, this mass. How fast is it moving? Xn dot, right, is the velocity. And square of this is the kinetic energy of the atom itself. Right? Plus, because it's a mass spring system, you can write it as a spring constant, big K, let's say, times xn. Does that make sense? Half kx squared is the energy stored in this spring. And if the spring is stretched out or compressed, here's the how much is stretched out or compressed, right? So that's the energy stored in the spring. So kinetic energy of the atom, potential energy of the spring, right? So this is the phonon part of it. And here, so this is a classical picture, right, of the energy of the phonons, of the heat. And when you go to quantum, all that you do is all of these become, basically mass times this velocity becomes momentum, this becomes x, and they fail to commute again, x and p. And this becomes exactly the harmonic oscillator. Right? The phonon part is the exact harmonic oscillator. And this one will become, let me just write it down. And I think harmonic oscillator, h bar omega q, right, times bq, dagger bq plus half. That's how the phonon will become. The total energy of the system is electronic energy plus phonon energy plus any exchange between them. Right? Any exchange between them, electron-phonon interaction. Right? So all transport phenomena is really tied to this picture that you have electronics energy, phonon energy, plus another term which is interaction of electrons and phonons. For example, so you'll have this term plus this term, and then you'll have some interaction, and electron-phonon interaction could be, here's an example in operator notation. Maybe you can tell me what am I writing physically, what does this mean? C, K, C, K, and C, K minus Q, dagger, and B, Q, dagger. And what is this process? So what does this mean? I am destroying or removing an electron from state K, right? I removed an electron from state K, right? And I put it in a state K minus Q, right? And so that it lost some momentum, and it also lost some energy, right? Lost some momentum, lost some energy. But all of that momentum and all of that energy was taken up, transferred to the phonon, right? Right, so this is the process that is an emission of a phonon, for example, right? So, and so on. So this is we're going to talk about this in a little more detail in the next class tomorrow. Okay?